Hey guys, welcome back to SGLang Office Hour. So today we're Alex from RadixArk. He's a new member of the SGLang community, and he's going to share his experience on getting his hands on SGLang projects. Welcome, Alex.
Hi, everyone. It's great to be here. And yeah, thank you, Kai. And yeah, so this is the first SGLang Office Hour I'm hosting, hopefully one of maybe quite a few. And today we're going to go over, I think, some general things like how do you navigate a kind of really big and complex code base, right? And also the kind of an overview of what does it actually look like to kind of go through and like piece by piece kind of assemble a mental model of what's going on in SGLang. And so, to that end, I've prepared some slides, and let's get started with the basics. So, what actually happens when you run Python SGLang launch server? How are requests actually managed when we call this launch server, right? And so at the highest level, this is what's happening. There's kind of like four key parts. There's this HTTP / remote procedure call server. If you've ever run the launch server command, you'll see right at the end, server is fired up and ready to roll at port 30,000 or port 40,000 for gRPC. And the HTTP server specifically is using fast API and a lightweight Uvicorn serving in Python. That's kind of important in terms of how we think about like what are the ways we can actually connect to SGLang, right? Does it support HTTP 1.1, HTTP 2.0, etc.? And that's all based off the fact that your core dependencies, which we'll find and investigate throughout this talk, tell you what you can support and what you can do, right? And so on the gRPC side, this is routed through something called the SGL model gateway, which we'll see is like another top-level directory in the SGLang repository. Then once a request goes through there, it's routed through our tokenizer and detokenizer managers. And for those who aren't aware, tokenization and detokenization are these like CPU-bound tasks and are usually offloaded to separate processes so they don't block the GPU scheduler. SGLang pioneered and is known for this like zero overhead scheduling, where you are planning what's happening next on the GPU while your current CPU cycle is running. And we'll go more into how this works a bit later. And so going into like the specifics, the reason why we have like separate tokenization and detokenization, even though they're like one-to-one mappings of one another, right, is for performance reasons, like when we do batch decoding or when you need to do like reasoning parsing management, things that are not part of the basics. So we'll talk about them a little bit later. And so from these managers, we move into like, well, how are the requests actually being managed, right? And so this relates to the scheduler, a little bit of the KV cache, right? But more importantly, from a ML systems perspective, the scheduler is probably a bit more important, which might be a hot take to some. And so the scheduler itself is this mixin-based approach, which if you're not familiar is you provide like a core set of primitives to a larger operating class. And it basically we do this because different hardware, which SGLang supports many, require different scheduling policies, right? I think a really classic example of this is like, imagine you're doing your prefill, which is really compute intensive on maybe like this world-class NVIDIA like Vera Rubin GPU, right? And maybe you only have your decode nodes in like an RTX like 4090, right? The way you probably want to schedule those two devices are a little different. And so there are many classic learnings around scheduling from ML recommendation systems, classic distributed systems. The two classic ones in terms of LLM serving that have now like evolved and are not used as much anymore, but are great for like interviews and stuff like this, are these concepts of like deadline-based scheduling, and then like how much has a request been processed. And this looks as your requests are an objective function of How can you take metrics and optimize for throughput versus latency, right? And so last but not least, we actually have to run the computation somewhere, right? And so these are our GPU workers. And so in SGLang right now, there is one process per GPU that controls what that GPU is running. This is an intentional design choice because you want to minimize contention per GPU worker, right? As like parallelization gets better and like things like tensor parallelism, which we will talk a little bit about later, get more thoroughly evaluated, you can look into this concept of what does it actually mean to run many things on a GPU? What does resource management look like? But for now, you can think of the GPU worker as like one SGLang process to one GPU. And so these are the basics. This is how you route through everything, okay? And so looking at this in depth, and this might be a little hard to see, so we can go over it later. But the key idea is that we have this client, and then from this client, we either have your HTTP server, your gRPC server, and they effectively are doing the same form of routing. This goes into the prefill nodes and your disaggregated inference, which goes through your scheduler, your tokenization, some KV cache transfer. And then from here, you have the same thing happening where your router has taken some requests to your decode nodes. You go through the same process with your scheduler, your detokenizer manager, and then your tokenizer manager, and then you get your final output. And this is the rough high-level request flow of SGLang. I made this earlier today, so hopefully I'll be able to answer any questions you guys might have about what this looks like in detail a little bit later. And so we've talked about the request flow, but what core components are actually happening when we're running these models, right? The other side of the coin. And so SGLang has this operation-based backend dispatch. And that's a lot of words to say that there are these general things that are very useful, like radix attentions, prefix caching, right? Or a mixture of experts. You know that you always are going to need to pre-process the weights, or flash attention maybe needs to be done, or maybe you want to use Triton, stuff like that, right? The fundamental mechanism behind each of these things is that this operation is still happening. And so this is what we mean by operation-based backend dispatch, where you can take the like big bottlenecks or big operations and represent them as these generic ops, which then can go to their relevant hardware, their relevant performance backend, or whatever's needed. And so next, let's talk a little bit more about worker orchestration. We talked earlier about how with the like one process to one GPU kind of like abstraction, right? But what's actually happening here is we aren't just doing that one process and like that's one request each time. The process itself is being fed from a ZMQ or a ZMQ process. And the idea here is we're trying to minimize what's called GPU starvation. And if you don't know, GPU starvation is, as it sounds, the CPU or some other process is working and the GPU is not. And so to achieve this, the ZMQ is managing your concurrency to your GPU from that one process. And the scheduler is what's coordinating the sets of processes with the ZMQ being the load balancer, right? And last but not least, the final core component that's important to talk about is the runtime orchestration. And this is when you are running LLMs in production and you're running SGLang, what are you actually doing, right? And so SGLang in production is going to run on a Docker image. And it can obviously run through scripts, other processes, right? But the goal with Docker is you have this reproducible, nearly hermetic build that anyone can use and pull from anywhere as long as it's on a registry, right? And so LMSys, the organization, provides nightly and daily images. Every time a new model is released, new version bumps, anytime like a major patch needs to be done. So a very big thank you to them. It's important that as development continues, we want to make sure that our customers, the open source community, are getting the best things the fastest as possible. And so let's like from this like worker orchestration, and I've also thrown in like this rough control flow between these slides. Let's actually kind of deep dive into the zero overhead scheduling that I mentioned that's kind of been floating around. So what happens here is that we have like these 3 actions, and these are all the like sub-description, so to speak, of these previous things. In the scheduler, we have this schedule batch, which exists on our CPU. We manage our request queue. We have our prefill versus decode, as shown in the diagram from earlier. And then we have our KV cache bookkeeping, allocation, prefix management, and then we apply our chosen scheduler strategy, right? Then on the actual model worker, the GPU process, we have like these serialized messages that are distributed to your GPU tensor parallelism workers or your data parallelism workers, right? And you have to pre-allocate your memory, deal with metadata, maybe like deal with kernel launch like overhead, all these kind of things that prepares the model to run as fast as possible when inference actually starts. And at like n equals 0, your forward batch is your first forward pass, and then at n equals 1 and greater, you are then doing these in a loop such that you get the zero overhead scheduling, that while this is happening for the next batch, this has already happened for the previous batch, or the reverse of that, and so on. And so yeah, that is like the high level details of what's all going on. And so to that end, what is SGLang actually built on top of, right? We now know the control flow, and I've like maybe mentioned a few dependencies around here, but we haven't actually talked too much about the ML ecosystem, right? This was just from a distributed systems point of view. And so the key dependencies you can view as PyTorch, Triton, Hugging Face, some token management stuff, and then some tensor management stuff, right? And so let's kind of deep dive into each. PyTorch, as many of you know, is a very popular machine learning framework, and it serves a whole host of purposes past LLMs. It helps in scientific computing, it helps in audio, it helps in vision, and the PyTorch itself it's a beast of a software. It's huge. And the key and important thing here is that you never want to try to fight PyTorch. If you're fighting PyTorch, that either means that the feature work just needs to be in PyTorch, or that you are doing something that is either really interesting or really needs to be evaluated. And I myself have fought PyTorch and learned this lesson the hard way. And then Triton is this machine learning compiler built on MLIR. And in some versions with like the CUDA version of PyTorch, and I believe the AMD like ROCm fork of that, the Triton comes as included in PyTorch. But PyTorch itself also, like before Triton in the 2010s, supported NVIDIA and AMD without Triton. Triton is just a means to an end. And this is important to recognize, as a lot of SGLang code is built on Triton, but it's just a way to write kernels, right? As we've seen this like kernel renaissance, there are many things that are going to like kind of come into discussion, right? The MLIR, for example, was originally built on XLA, or built for XLA, excuse me. And then it has now become this massive sprawling thing that has implemented Triton. It's also behind TileIR or TileLang. It's also behind, if I'm not mistaken, CUDA-Tile or Qtile. It's also behind QTSL. All of these are fundamental like pieces that NVIDIA or other competitors in the hardware space have provided. And there is, I think, a clear trend that as we kind of continue to optimize for performance, the layer at which we expose basically different primitives up and below the compiler that we use, so in this case Triton, have changed, right? They're like, if you are very active on Twitter, you may have seen like, oh, Triton's not so performant on Blackwell, and like they made Gluon. I can go on and on. That maybe that can be another talk. But the important thing to understand is that from PyTorch, from Triton, we have to lower to the actual meaningful thing, the meaningful primitives that our hardware uses, right? So for NVIDIA, that's CUDA, that's PTX, right? For AMD, that's a different stack with ROCm, right? For all of these hardwares basically still have to lower to their compiler backends, which optimizes for their own hardwares. And so Triton is the most popular way to do this. And right now, I think there's more I'm going to talk about a little bit later for that. But moving on, Hugging Face, as many of you know, is where you get open source models from, and it's kind of like the main name in town for anything relating to like safe tensor storage. And the transformers library that they offer is kind of a first step in when you put a model on Hugging Face, you want people to be able to take Hugging Face and run your models, right? So it's supposed to, in some sense, be like the community's like ground truth on what a good model looks like. And so in practice, this looks a little different, but I think it's very useful to understand what is transformers actually there for, right? And transformers is very fast in some ways and not so fast in others. But the important thing is that day zero support runs through Hugging Face for PyTorch, right? Because the transformers library does not support JAX, does not support like NumPy, it supports PyTorch. And this is important to understand that like when you look at SGLang, when you look at VLM, when you look at things like ZML, all of them are like working with Hugging Face and these model providers to make sure that the model implementation is correct, that it looks like we see reproducible results and like in a sense empirical reproducible results across multiple implementations. And so day zero support, at least on the SGLang side, is kind of twofold, right? We talked about this Docker image earlier. And the Docker image provided from LMSys in the SGL cookbook, which I will say is absolutely fantastic. If you guys haven't looked at the SGL cookbook recently, some changes were recently pushed. I'll think I can drop the link in the chat at some point because it's absolutely great. But you have the Docker image, and then you have the model actually being supported on like the main of the GitHub, right? And these are two things, because when any of these dependencies don't support a model being released, right? That takes like dependency work that may take longer to get on main than it will take to be in a Docker image, right? I think there are plenty of good examples of this, and I think if you like look hard enough, you can see where like, oh, this PR took a day or two, whereas the Docker image was out immediately. And so now we've kind of talked about PyTorch and Triton, which is how we write our models and implementation. Hugging Face is where they're stored, and transformers is almost like this ground truth of implementation. But what does it actually look like as the hard dependencies of running these models, right? And so this relates to token management with like structured outputs with X grammar, sentence piece, word piece, byte pair encoding. All of these are the fundamental ways like if you were to break down token factories, you can't get tokens without tokenization, right? And so this is a hard dependency of language models themselves. There has been some interesting research on hierarchical or HNets, but I think that's a conversation for the future. And last but not least, excuse me. Last but not least, we have like these weights, right? So we talked about in Hugging Face, this is where the weights are stored, but what's the actual file format, right? And so time and time again, there have been all these different ways to store them. Originally, before like my favorite question is, before Safe Tensors, what was there, right? Because Safe Tensors has become an industry standard. But before Safe Tensors, people were loading like these bin files from PyTorch exports and having to like separate the weights out onto disk. So Safe Tensors was like this very revolutionary thing when it came out. But so you look at all these different tensor storage operations, and these are also fundamentally very hard dependencies, right? For example, if Safe Tensors was to put out a version change that no longer worked with SGLang or no longer worked with VLM, et cetera, that would take a lot of time to figure out, right? And so I think another good rabbit hole is looking through like load format, enum, and SGLang and seeing all the different ways these like weight formats kind of exist, right? Because there are, I think 12 of them. And this all in all is like, I think, a really good like education on what does the actual ML ecosystem look like if I wanted to serve a model in production, right? And so I think this kind of tops off the first part of this, which is like, what does SGLang do? What are the hard dependencies? And what actually needs to be understood to really start developing, right? I think that whenever you approach a code base, you can view it in like 3 different lenses: the like dependency lens, the like, okay, let me trace through everything very specifically. And I think the age of AI has really changed that. And then I think last but not least, it's like, oh, I know I need to get like this one thing within this blast radius and I need to get it done. And I think as you build your world model for these things and like how these exist, of like, oh, the SGLang is using PyTorch and Triton to make sure that the attention works, and this model maybe doesn't work with here, so it's loading from transformers, and so on and so on, right? These are all things that like enrich your world model of how all of this stuff really works. And so to that end, I'm going to talk also a little bit about now that we have like a basic idea of how SGLang works, what are some like short-term ideas and long-term ideas to make SGLang even better? And so some of this is some of the work I'm doing at RadixArk. Others are just like my personal ideas of things I think would be cool. And so in the short term, we can view this as, I think, a few like easy goals and a few like maybe harder goals. I think some very easy wins for SGLang are like looking at A/B testing Thunder kittens, hip kittens. If you guys read the Cursor technical report that came out, I guess yesterday, you'll see that they actually use Thunder kitten kernels in production. And there's been a lot of work from the community as a whole to see like what is the best way to write kernels. And I think Hazy Research has an interesting direction. And A/B testing something is a relatively like cheap mechanism as long as you can afford the GPUs. And on this kind of same note, there is another idea here which I don't have on the slides, which is enabling like CPU development. And this kind of falls into the making multi-hardware onboarding easy. But right now, if you like wanted to locally develop SGLang on your Mac, you can't. And this is because of Triton is not available for Macs. And so if we make Triton a soft dependency, or we minimize its blast radius, we unlock many different people who want to contribute to the core engine of SGLang and can work on their Mac or their Windows computer or so on. So I think that's also a very important short-term idea. And that leads into this like making multi-hardware onboarding easy. Right now, SGLang supports, I want to say 9.5 hardwares. The half is the Mac Metal stuff is in progress. But we want to make the onboarding easy, right? This idea that there's like out-of-tree hardware that is very hard to like manage is really not true, right? As long as you have good abstractions, you should be able to make multi-hardware onboarding quite easy. And to that extent, like speaking of like what are some other perf gains, this kind of naturally segues into what does TRTLM do? And SGLang also does this. They have these like fake ops that exist, and they point to the direct kernels, they point to the direct processes. And I think if you ever have a chance to look through the TRTLM code base, they have some fantastic kernels. I mean, NVIDIA, fantastic kernels, I wonder why, right? But with TRTLM, they have this, they have mixture of experts kernels, they have like enhanced LoRa kernels, and we already have like the support for like shim, ops, and torch in SGLang. I didn't really cover exactly what this means, but we should bring in some of these to see what the perf improvement looks like. Kind of falls into the same idea of like the A/B testing of the Thunder kittens and Hip kittens and all that stuff. And then last but not least, I think we would have a major win, and this is something that's already been implemented in SGL diffusion by reducing the serialization overhead for how we pass messages. As I mentioned earlier, ZMQ is a major dependency, and we do serialization between these different processes. And right now this is in Python, so which if it's pickled, if pickle is like the Python compression library or Python serialization library. And so pickle is we'll grab all the fields and all of the like metadata, even if you don't need it. And so we are a little harder on what's actually serialized. We can minimize the actual messages being sent to only what's needed, and we'll see a pretty nice speed up. In the long term, I think there are more interesting ideas. Right now, and this is relatively industry standard, the bleeding edge is where we have speculative decoding draft models that are tied to our prefill and decode inference, right? But there has been some really experimental work on heterogeneous nodes. So basically, there's another set of nodes in that diagram I showed earlier that would allow for speculative decoding to work as its own set of model and its own set of hardware. And this is really important because the industry is trending towards heterogeneous compute. And if any of you like had watched the GTC keynote or anything like that, you would see that the Vera Rubin platform also kind of operates under this idea where if you could have like your draft model on like the Grok chips, right? And separately, you could also have your decode on the Grok chips, right? You then have like the premise of like two independent processes from your prefill being super fast. And your prefill is already super fast if you're using a compute-intensive device. And so this is something that pushes the frontier further. On this same kind of like speculative decoding path, I would want to do like a little bit more research because I think that there are many different forms out there, and the industry standard has been Eagle 3, which SGLang supports. But there are a lot of interesting approaches to these like test time learning mechanisms for speculative decoding. So the speculative decoder learns with enterprise workflows or your workflow. So it's better at knowing you or better at knowing the batch of you. And so having deeper support of this, I think would be very important. And also I think it's a feature that like real customers want, right? Because it allows these LLMs to have a layer of adaptability, which they currently do not have. And kind of talking about the data and what that looks like. Right now, SGLang supports Mooncake, which many of you might have heard of, Nixel, and these are all the ways we do RDMA transfers between stores of memory. And I think there's a more interesting, more performant direction that also can help here. There's things like OpenUCX. There's some other interesting research where you can actually tie the handlers for some of these processes within your kernels, so you don't have to pay for the overhead of your KV cache transfers, or you pay less for the overhead. And so this is I think a little bit of a technically complicated idea, but I think it's worth exploring. And then last but not least, as we talk about like hard dependencies earlier, right now we support Torch, but in the future, it would be great if we could support Torch graphs, right? And Torch graphs look like Onyx, they look like OpenVINO, and these fundamentally are really important. Where right now we do a lot of CPU-based processing, right, and that runs through these Python processes. However, if we could treat these as OpenVINO graphs of like the parts where we move tensors around, we schedule tensors, right? And we're moving tensors to GPU. We don't actually have to pay for the Python overhead. We are paying for the CPU processing to the GPU, and that's it. And so that's another, I think, long-term performance improvement that would be not only highly interesting, but highly relevant in the frontier of what needs to be done. And yeah, I think that is the most of what I want to talk about today. I think there's a ton of interesting directions to go. As a final little blip, RadixArk is hiring. If ML systems are interesting to you, if any of what I talked about is like something that you find like, oh my God, this is amazing, this is like what I want to work on, I encourage you to scan the QR code. And to that end, let's start the Q&A.
Hey, let's do Q&A. I already see someone on the comment mentioning about we should add MLX backend to that. Yeah. What do you think about that?
Yeah, so I've been reviewing some PRs on the MLX backend, and I think there's some nuance here. I think that like MPS MLX is not the like exact distinction that we're looking for, right? We effectively just want a way to run basically these models as effectively on the Mac devices as possible, right? And so the way I at least look at it is there's been some work from the open source community on like tensor bridges for like zero overhead transfers between Torch and MLX. And if that works for 90% of things, that's great, right? At the end of the day, right, we don't want to have a situation where there's like a metal kernel for every single thing in SGLang, right? Metal kernels are I don't think are very clear in how they actually work. And also there's some other fundamental incompatibilities with MLX and the idea behind KV cache, where MLX is a unified memory, and you have to roughly use like we already provide these tricks in SGLang where you can set like static total memory, etc. But it's important when you look at how this integration works. I think that there's a few different wrinkles that we're actively working on.
Great. Yeah, let's wait for more question. And before there's a new question coming in, so have you used I know you just like get started with the SGLang. So what do you think is the most helpful material, like the SGLang cookbooks or the docs? Which one do you like look most, or like what do you think about that?
Yeah, I think that the docs themselves are very good. For me, I think that my first entry was understanding, like from the cookbook, all right, what is actually being provided to me? And then I wanted to establish a very ground up understanding. But I think the docs are good enough that for someone who's a complete, like they have no clue how some of this stuff works and they want to gain some basic understanding, I would encourage them to use both the docs and the cookbook.
Perfect. We have a new comment asking about ever consider Vulkan.
Yeah, so I think that there's like some nuance here. Nuance relating to specifically what the Vulkan runtime does. And Vulkan by itself is something that can be treated as like a compiler front end for what's running on a GPU. But from another perspective, it can just be treated as like a processing library, right? And I think that the problem with Vulkan, at least for modern scientific computing, is that Vulkan will never be as good as just spending the time to write out your NVIDIA, your AMD performance work itself. I think like in the same direction, there should be some work that we do on, like, if you're familiar with IREE, IREE, that like having basically some form of like generic compiler backend in the future may be somewhat interesting. But this also kind of goes back to the idea of like, once we consider that, we should also be considering MLIR and some other like really fantastic things, right?
Okay, next question. Had you guys considered UMA awareness for MLX and Jacksons?
So by UMA awareness, could you tell me exactly what you mean? I feel like that can be a few acronyms.
Yes, and I have a question. So could you go through the workflow when a new model is launched every time, especially any challenge or bottleneck for that? Thank you.
Yeah. So the new model support can be viewed as like 3 distinct steps. The first step is what are the actual like hard dependencies of the model? For example, with Mistral Small 4, they have the custom tokenizer, they have their own custom weight loader, right? So it's making sure that like their hard dependencies work in SGLang, right? And then at that point, you know that the basically surrounding factors now work, right? And so it's now, what are the end-to-end mechanisms that need to be supported, right? So this is such a variable thing, right? Like when DeepSeek v3.2 had come out, right? That was a ton of model work, right? But comparatively, when something like Llama 3.2 came out and you already support Llama 3.1, all you had to do was make sure that you support clamping and pretty much the same model, right? And so to that end, you figure out what does this model need to work well, and what abstractions do we have, what abstractions don't we have, right? And this is kind of what I mean, like with the Docker versus mainline kind of access, where there is work to be done when you want to provide like the Docker image quite quickly, and you can patch something and you can say, all right, this works, we know it's performant. But in the long term, maybe you're not putting that patch on mainline because you want to have it like fully integrated into things like your attention dispatch, your mixture of experts dispatch, right? So you now have like, you deal with the model's own dependencies, the model's own mechanisms. And then last but not least, you're doing evaluation, right? Like speaking, I had worked on the Mistral Small 4 model support. And I think a really good example of this is that we were noticing that it didn't perform well on MMMU, which is the multiple choice multimodal benchmark. And the reason why it wasn't performing well was not due to our implementation. It was due to the fact that the way that we were doing the request template from the model was improperly formatted with the Mistral style of like inputs. And so that's a fundamental fix that had to be done for SGLang. And so like through these 3 steps basically, which is like, again, deal with the model's dependencies, deal with SGLang's mechanisms, and then deal with the basically performance optimizations, evaluation, benchmarking. We want to make sure we're serving the perfect model. You have these kind of 3 steps.
Wonderful. Next question, someone asked, like, could you share how do you build up the ground understanding and trace flow in such a large code base?
Yeah, I think that there's kind of like three things. One, like kind of if you've ever lifted weights, you may have heard this term like called progressive overload. You need to slightly challenge your brain to just see the forest a little bit. And what I mean by that is it is important for like certain things to like understand to a very fine detail. Like I probably have like a few lines of code memorized in my head from when I was looking over the tokenizer manager. Don't let me stay here and like say that I don't do that. But the more fundamental idea is like, oh, I know that the tokenizer and scheduler, they share this kind of relationship. The scheduler and the detokenizer share this kind of relationship, right? And so as you kind of build there's two forks in the road here. As you take on small issues and you realize connections, and then you do enough small issues, you see the forest. Or conversely, I will say this, without the help of AI to at least get your rough draft out, try to tackle from like a really good issue, like, oh, this needs to be designed, deep dive that and say, all right, well, we need to design this like new mixture of experts module for SGLang. Where does mixture of experts currently sit? Why does it look like how it looks like? And what are the actual pieces you're putting together, right? The only 2 ways people ever understand software is if you're dogfooding it or you're investigating it, right? And dogfooding is still like something that you have to actively say, like, all right, I've tested this out, I understand the in and out from a black box. How can I minimize the black box radius, or even like distribute the sets of black boxes from like one big to many small ones?
Oh, just one random question. Do you use like Cloud Code or Codex or anything to help you understand?
Yeah. I'm a like cursor person at the moment. Right now, the office has been on a big Claude Code push. I actually was trying to use a Claude Code or like the Claude workspace for the slides. It didn't work out well, but I got to like play around with some diagrams. Thank you for the so UMA is the unified memory architecture. So this is what I was talking about earlier. basically whenever you try to launch a KV cache or the same process, it's all shared, right? And you don't actually care like let's kind of like talk about like our compare and contrast like the pure Linux to like the Mac case, right? Linux has like this idea of like NUMA affinity and like you can find the best cores to do the best jobs, right? The unified memory architecture and like the PSUtil for Mac don't really care about this. And what I mean by this is that your unified memory architecture, your weights, your KV cache, they're all going to live within the same area. And you can't say, oh, I need, unless you pre-allocate, you can't really reasonably estimate what's going to happen during runtime, right? You can only do like this pre-allocated cache with MPS or with MLX. There is some work that like the MLX team I think is working on to make this a bit better, but you basically just to be very careful with your memory when you run on a Mac device.
All right, next question. Oh, this is
Yeah.
So how does SGLang decide which model to support? I would love to run the Momo 2 model with SGLang. This one from Allen Institution, right?
Yeah. I think that there's two things. One, if you can let us know ahead of time, like for example, when you're supporting a model, some of them, as I said, the Llama 3.2s of the world are easy, right? But some of them take these longer, drawn-out efforts to deal with like the certain non-trivial mechanisms of these models. And what I mean by that is like look at Flux, look at One, kind of the same area as Momo L2. I think that it's not a question of decision; it's just a question of what do we know and when do we know it, and how long do we estimate that it will take to support? Because we want to support all the models as soon as possible, and we want them to like the best inferences on SGLang, right? And so to that end, we want to make sure that new model support looks as strong as it is, and ideally day zero for everything.
All right, next question. Andy, what's the workflow for kernel engineering and optimization? What's the time ratio typically spent on improving existing popular kernels and writing new kernels?
So I have probably like a bad take here. I think that when we talk about the time ratio spent on popular kernels versus new kernels, it doesn't really matter. Effectively, what matters is your performance graph. The key idea here is like, yes, there are some like little short-term things that you can do, like the Thunderkins versus Hipkins, which I was talking about earlier, right? But fundamentally, if your flame graph looks really good and you're like, oh, well, like we've now optimized this model so much that the CPU is for some reason the bottleneck or the data loading is the bottleneck, right? Those are fundamental things that you just need to address, right? This has nothing to do with the actual like classic math behind the kernel itself, right? And so this kind of goes into my topic of like ideally some of these like things that become bottlenecks once you optimize models to like the P95 or the P99 will be achieved through like kernel interop, and that shifts the bottleneck again, right? I think the workflow for kernel engineering and optimization is that you like naively look at this graph for support, and from this graph you say, all right, these are my bottlenecks that I've looked at and I've observed empirically. You fix those, and after that you keep on doing it until you've reached a reasonable target of performance. In general, some kernels are very easy, right? Some kernels are very hard, right? When MLA first had to be supported, that was a multi-month effort, right? But comparatively, ever since the MLA backend has been properly integrated, supporting new things for MLA is less of an engineering challenge than like the goal is you have like these compound gains over time, no matter what part of software engineering you're doing.
All right, next question. Are there other benchmarks for SGLang team used to evaluate VLM models beside MMU or, for example, OCR bench?
Yeah, so if you look through the benchmark folder of SGLang, you will see that there is this run eval function, And there's a set of comprehensive benchmarks. There's, I believe, a few different OCR There's a few different OCR benchmarks. There's obviously MMU, MMLU, MMI, I think, GSM-8K, the extended GSM-8K. I think there's like a good 20 of them. And so when we're looking at this, the way I at least think about it is like GSM-8K tells us, okay, text is like working. Like the capital of France is Paris. Okay, we have the model working. And then as you like kind of go down the benchmark stack, you see the idiosyncrasies of maybe your implementation, maybe the model, and so on.
Great. One last question: mic or no mic on Cloud Code? I think this is referring to the voice input.
Yeah. The Whisper Flow people have like demoed this. I think it's so cool. My thing with Cloud Code is I like asking a lot of tangents when I code, like the / by the way. And for me, that doesn't really like go well with mics because I have like multiple forked chats, like, oh, by the way, does this look right? By the way, how does this work? Or by the way, etc. Right? And so for me, no mic.
All right, that's it. This is the Q&A for today. And if you haven't followed us on GitHub and on X, please scan the code and do that. And also now we have a Luma calendar. We will just put all the meetup and office hour like this to this calendar. Please go to this link and follow that. And thank you so much for being here today, Alex, and everyone who is watching the stream. See you in the next office hour.
All right. Bye, everyone.